All right, so I'd
Great.
like to welcome today's speaker, Nicholas Williams, who's going to talk to us about oriented matroids from cluster tilting objects on type A cluster categories. So thank you, Nicholas.
Thank you very much for the introduction, Franco, and yeah, thanks for the opportunity to speak today. I changed the title slightly from the abstract, but it's still the same content. Um, so this is about work that I did last year. And perhaps the starting point of this work is this well-known theorem of Fomin and Zelevinsky that says there is a bijection between, on the one hand, clusters in the AN cluster algebra, and on the other hand, triangulations of a convex n+3 gon. So this was one of the very early explicit descriptions of a cluster algebra introduced by Fomin and Zelevinsky. And there is, I suppose, a categorical version of this bijection. So instead of clusters in the AN cluster algebra, we can have basic cluster tilting objects in the AN cluster category, which I'll write like so, up to isomorphism. I suppose this is originally due to Calderon, Chapoton, and Schiffler. So this cluster category was first defined by Buan, Marsh, Reinecker, Reiten, and Todorov. So given an acyclic with a Q, the authors I just mentioned, Buan, Marsh, Reinecker, Reiten, and Todorov, defined the, oops, what's that? Define the cluster category, which are denoted CQ. So it is defined using the bounded derived categories of the path algebra of the quiver Q, where K is some field. So it's the category of orbits of the Serre functor combined with the negative second shift. So I'll give some explicit example of this later, which hopefully will be helpful if you haven't seen this before. So yeah, this is also a triangulated category. By work of color. Okay, so the starting point for the work I'm talking about today is this three-dimensional version of the above bijection, which is from earlier work from my PhD thesis. So this is a three-dimensional version of the above bijection. So there's a bijection between now some three-dimensional triangulations, so namely triangulations of a three-dimensional cyclic polytope. So yeah, just some three-dimensional polytope, three-dimensional shape. the exact definition of this won't be important for us in this talk. But yeah, some 3D shape with n plus 3 vertices, and the algebraic objects on the other side of the bijection are these so-called maximal green sequences. So I'll define these later in the talk, of linearly oriented AN. So yeah, just this quiver up to some natural equivalence relation. So the starting point for the paper I'm talking about today is the following question. So does this hold for other orientations of AN? Which is to say, is there some three-dimensional polytope, three-dimensional shape, such that its triangulations correspond to equivalence classes of maximal green sequences. And I don't per se actually answer this question in the paper, but I go some way towards answering it. So instead of answering this question for a polytope, I find some abstract version of a polytope, which is something called an oriented matroid, and I'll talk more about this later. So one can think of this as somehow the abstract version of a polytope. So every polytope has this associated structure called an oriented matroid. So every shape has this. But not all oriented matroids can actually be realized using polytopes. So I answer actually maybe even a stronger version of the question. So stronger version of the question. Instead of for all orientations of AN, you can ask this for all cluster tilting objects. In the AN cluster category. And yeah, I'll define all of these terms in due course. Okay, so let me state the main theorem. So yeah, this is the theorem that goes some way towards answering this question. So for every cluster tilting object, T in the cluster category of AN, there is an oriented matroid. Should I mention it? M of T, such that there is a bijection between, on the one hand, triangulations of MT, which is something that still makes sense for oriented matroids. You can talk about their triangulations. And on the other hand, maximal green sequences of the endomorphism algebra of T in the cluster category up to equivalence. So in particular, sorry, I forgot actually an assumption to this theorem. So actually, yeah, we need an adjective here, which is stackable. So I conjecture actually that all triangulations of this oriented matroid are stackable, but yeah, I was only able to show the bijection for the stackable triangulations. So in particular, yeah, when T corresponds to the linear orientation, this specializes to the previous theorem. Okay. So that's an overview of what I'm going to talk about. So yeah, let me now give you a bit more detail. So yeah, let me talk maybe a bit more about cluster categories. So I defined these earlier, but I didn't yet tell you what a cluster tilting object is. So let me do that now. So these are defined by Bulan-Marsh, Reinecke-Rayton, and Todorov. So an object T in the cluster category CQ is said to be cluster tilting if firstly x1 between T and itself is 0. And secondly, if T has as many isomorphism classes of indecomposable summands as there are vertices of the quiver. Okay, so I'll give a sort of explicit combinatorial description of these in type A, which is of course the case we're interested in, and then I'll do an example, which will hopefully make things a bit more concrete if you haven't seen this before. So type A cluster categories were really first introduced slightly before the work of Bulan-Marsh, Reinecke-Rayton, and Todorov by Calderó, Shepperton, and Schiffler. And to make things easier, I'm going to denote CN to mean the cluster category of AN. And the objects in the cluster category admit the following combinatorial description. So I'm going to label the vertices of a convex n plus 3 gon anti-clockwise. Then we have a bijection between, on the one hand, diagonals AB in this n+3 gon. These are in bijection with the indecomposable objects. M, A, B in this type A cluster category. And this kind of combinatorial description gives us some information. So namely, MAB shifted by 1. So yeah, the cluster category is triangulated, so it has this shift functor. This corresponds to MA-1, B-1. And furthermore, this description of the objects allows you to tell when x1 is non-zero. So this happens if and only if AC and BD cross. And somehow a corollary of these facts is that, yeah, we have this bijection I mentioned at the start between triangulations of the n+3 gon, and on the other hand, basic cluster tilting objects in CM. And this can be seen as follows. So a cluster tilting object is one which has no x1 with itself. So it corresponds to a set of arcs which do not cross. And a triangulation of an n+3 gon contains n diagonals. So we get that a basic cluster tilting object corresponds to a set of n non-crossing diagonals by definition of cluster tilting object, and then that precisely gives us a triangulation. Okay, so let me sort of give you an explicit example of the cluster category for A2, so you can see a bit more what it looks like. So the A2 quiver is as follows: this arrow with 2 vertices labeled 1 and 2. It has the following indecomposable representations. So you have 1 corresponding to this representation. This representation, I'm going to label 1, 2. K to K. And yeah, finally, this representation I'm going to label 2. And so we can draw the so-called Auslander-Rosen quiver of modules over the path algebra of A2. This namely has, draws these 3 objects and the irreducible homomorphisms between them. So there's one from 2 to 1, 2, and then one from 1, 2 to 1. If we now look at the bounded derived category of A2, so this contains a copy of the module category, and then all of the shifts of the module category. And of course, homomorphisms to shifted objects correspond to extensions. So that's why we get a homomorphism from, for instance, 1 shifted by -1 to 2. And so on. Okay, so now we have this Serre functor new I mentioned earlier. So this acts on the category as follows. Sort of moves things just along one. And the cluster category Cn is defined to be the category of orbits of the Serre functor composed with the second shift. So okay, let's first take the orbits corresponding just to the complexes concentrated in degree 0. Now, if I say consider this object one shifted by -1, then, for instance, new inverse sends it to here, and then the second shift is going to send it to here, so that in fact, these two objects are in the same orbit. And if they're in the same orbit, they correspond to the same object in the cluster category. So in fact, if we take 1, 2 shifted by 1 as a representative of the orbit, then that's the next object that goes here. And in fact, these 5 objects give a fundamental domain for nu shifted by -2, i.e. every object, every indecomposable object, I suppose, has an orbit representative amongst these 5 objects. So I can draw the Auslander Rising quiver of the cluster category like so. It just cycles back round. It has these 5 indecomposable objects. So of course, if we look at our n+3 gon, then in this case, this is a 5 gon, i.e. a pentagon. So it indeed has 5 diagonals corresponding to the 5 indecomposable objects. And so, yes, one can make the following identification between the diagonals and the objects. So M13 can be 2, M24 can be, 1, 4. Can be 1, 2, 2, 4 can be 1, and 2, 5 can be 2 shifted by 1, and then finally 3, 5 is 1, 2 shifted by 1. And you can verify, for instance, that X non-vanishing corresponds to the diagonals crossing, and that cluster tilting objects correspond to triangulations. Okay, so that's maybe enough background on cluster categories for now. So let me move on to one of the main objects of the main theorem, namely maximal green sequences. So these were, I suppose, originally introduced by Keller And yeah, they moreover have many definitions. And yeah, the definition I'm going to present today is a little different to the usual definition, but it's the most useful one for my purposes. So today, we'll give definition using X triangulated categories. Yeah, which I won't define, but I'll give you enough of a flavor that hopefully the definition makes sense. Okay, so what are X triangulated categories? So firstly, I should say that these are introduced by Nakaoka and Palu. And the usual example one can think of come from extension closed subcategories. Of triangulated categories. Another way of thinking about these, which is maybe my perspective in this talk, is that they can be thought of as the triangulated analog of exact categories. So for exact categories, we have some sort of distinguished class of exact sequences which we work with. And in X triangulated categories, we have some, and those exact sequences in our exact category that we want to consider might somehow not be all of the exact sequences. And similarly in X triangulated categories, can consider a subset of the triangles of a triangulated category. Which gives the X triangulated structure. So yeah, hopefully this will become clearer in the following example, which is going to be important for us. So yeah, we will take the following new X triangulated structure on CM. So yeah, CN is a triangulated category, as I said. So it comes with some class of triangles, and we're going to put a sort of new X triangulated structure on it by taking a subset of those triangles. So yeah, let T in Cn be a cluster tilting object. Yeah, and what we're going to do is we're going to now consider the triangles x to y to z to h to x shifted by 1 such that h factors through t shifted by 1. So yeah, this is an example of a relative X triangulated structure due to Hirsch and Liu and Nakaoka, and it first appeared in the work of Padrol, Palu, Pilot, and Flamondon. Okay. So yeah, I'm going to denote by mathbold E sub t zx the set of equivalence classes of such triangles for x and z. Yeah, and yeah, one should somehow think of this as some kind of x1. And yeah, part of the point is that if one does this, this makes t projective. So yeah, by only considering a subset of the triangles to define our x1, we've kind of forced t to become a projective object. Okay, so I can now use this to define what I mean by maximal green sequence in this context. So yeah, I'm going to let L and L prime equal to E plus Y be two basic cluster tilting objects with x and y indecomposable such that yeah, there's this set is non-zero. So yeah, this sort of relative x1 between y and x is non-zero. In this case, say that L prime is a T green mutation of L. And now I can say what a maximal green sequence is. So definition. So yeah, a maximal green sequence of T, which you could also call a maximal green sequence of end of T, but I find it most convenient to think just in terms of T, is a sequence T equals T0, T1, up to TL equal to the shift of T of basic cluster tilting objects such that for each I Ti is a T green mutation of T pi minus 1. Okay, I mentioned earlier that there's an equivalence relation on maximal green sequences we have to use. So let me tell you what that is. So two maximal green sequences of T are said to be equivalent if they have the same sets of indecomposable direct summands. Okay, so let me maybe restate the theorem.
Sorry, Nick.
Yeah.
This implies that you do sort of the same mutations, but maybe in different order.
Yeah. So that's exactly right. So yeah, it's that's actually an equivalent way of defining this equivalence relation. So it's exactly the same as same mutations, but different order.
Right. And slightly more technical question, follow up. Do you know if the triangles or the X triangles that you get are exactly the same?
Yes, because you mean the like exchange X triangles?
Yeah.
They are the same up to scalar.
I see.
Thanks for the questions.
Yeah, cheers.
So again, this theorem from earlier is that there's a bijection. Now we know what this means between maximal green sequences of this sort of canonical cluster tilting object given by the path algebra of linearly oriented AN. So the image of the projectives over this algebra up to this equivalence relation and triangulations of some three-dimensional polytope, called a cyclic polytope. With n+3 vertices. So maybe just to do a quick example, just in the A2 case. So you remember the cluster category looks like this. And there are two maximal green sequences of two direct sum 1, 2, which all of the cluster tilting objects here correspond to the linear orientation, but this I guess is precisely the image of the projectives. So namely, there's the maximal green sequence where we mutate at 1, and then we mutate at 1, 2, and then we mutate at 1 again to get 2 shifted by 1 and 1, 2 shifted by 1. So now we've arrived at the shift of this cluster tilting object T. And then the other one, if we now mutate at 1, 2 instead, we get 2 plus 1, 2 shifted by 1. And then if we mutate at 2, we get 2 shifted by 1 plus 1, 2 shifted by 1. And one can, for instance, see that these two maximal green sequences are not equivalent on the definition I gave, because the first one has 1 as an indecomposable summand, and the second one doesn't. And you can also see that we've done different mutations. I should say that this result is in a joint paper of mine with Misha Gorski. Okay, I won't try and draw how these extend to three-dimensional triangulations. Now let me talk about the main result. So how to extend this theorem to other cluster tilting objects. So here's the question again. Maybe phrased slightly differently. So given an arbitrary basic cluster tilting object in Cn, is there a polytope, maybe I'll call this T, PT, such that triangulations of PT are in bijection with equivalence classes of maximal green sequences of T. Here's kind of the reason why this is maybe a difficult question. Polytopes are hard to realize. By which I mean, it's sort of often hard to explicitly write down a polytope which has the properties you want. But also, write down specific coordinates, for instance. And it's partly because, polytope contains more information than necessary, because, you have all of the positions, the precise positions of the vertices, but, we're really interested in, the essential combinatorial structure. The combinatorial information we are interested in is encoded in a structure called an oriented matroid. Let me give you a bit of an idea of what these are. So I'm going to let E V1 up to Vn inside R to the R just be a set of non-zero vectors. Then the oriented matroid and this way of presenting oriented matroids is also called the chirotope of E is the map chi from e to the r to the set -1, 0, 1, which sends this tuple of our vectors to the sign of the determinant. Maybe I'll give myself more space here. The sign of the determinant with columns vi1 up to vir. I guess here I want to take n greater than or equal to r. Yeah, here r is called the rank. So somehow, if we were to forget the signs here and just remember which subsets of E have a non-zero determinant, so which subsets are linearly independent, then what you get is just the sort of unoriented matroid. So it's remembering the signs that makes it oriented. Okay, so the point is for E an abstract finite set, so not necessarily a set of vectors, one can define an oriented matroid on E to be a map chi, again from e to the r to the set -1, 0, 1, satisfying certain axioms. And yeah, I won't spell out the detail of what precisely the axioms are. But yeah, somehow maybe surprisingly, given that the structure looks quite simple, turns out there's quite a lot one can do with this. And in particular, one can define triangulations of these. In a way that generalizes triangulations of polytopes. Okay, so let me tell you how to define an oriented matroid from a cluster tilting object in the AN cluster category. So these are the oriented matroids we're going to be interested in. So let T be a cluster tilting object in Cn. We define the following rank 4 oriented matroid on just the set from 1 up to n plus 3. So yeah, I'm going to let A, B, C, D be just some ordered subset of this. Sorry, that's supposed to be a 3. Okay. So what's the definition? So yeah, it's using this X-triangulated structure we had. So chi t, chi t of ABCD is defined to be +1 if these relative extensions from MBD to MAC is non-zero, and -1 if MAC to MBD is non-zero. If A, B, C, and D are all different, it's actually never zero. Yeah, so it's somehow determined by these relative x triangulated x in this way. So I said that this map has to satisfy certain axioms. So obviously that's not immediate, but one of the other theorems of the paper is that in fact chi t gives a well-defined oriented matroid. And secondly, the main theorem I wrote at the start is that there's a bijection between, on the one hand, stackable triangulations of chi t and maximal green sequences of t up to equivalence. So maybe this is a good point to stop.
Thank you.
Thanks.
Thank you very much. That was very interesting. Do we have any questions from the audience?
Yes, I do. I have many.
Far away.
I mean, there are two obvious questions that I would ask. What about the n?
Yes.
And what about general algebras of finite type?
It's a good question. So I think there should definitely be a story which is similar for other algebras which come from surfaces. For instance, Dn or gentle algebras of finite type. One should somehow be able to construct, instead of a three-dimensional polytope, I suppose, some sort of three-dimensional manifold with boundary whose triangulations correspond to equivalence classes of maximal green sequences. The nice thing about the AN case is that it's quite rigid. So in the AN case, you can think of it as your polygon as a disk with boundary, but you can also just think of it as a polygon, and all of the lines involved are straight lines. And
right.
In a similar way, like when you look at these three-dimensional triangulations, they're all triangulated by simplices with edges which are straight lines. When you go to more general cases of algebras from surfaces, then you're going to start to need to consider lines which are not straight.
No, but I mean, what if you consider just the case where you have a quotient of AN, right? I mean, sort of an Akiyama.
Quotient of AN, I mean, I guess, are you thinking about a quotient which is still gentle?
Yeah. For instance, I mean.
So I guess I would have to think about it, but I guess
it's like
that should also, if you, so that will come from, I guess, like a tilting object in the derived category. And then if you look at the image of that tilting object in the cluster category, then you get a cluster tilting object. And there must presumably be some relation between maximal green sequences of that cluster tilting object and then maximal green sequences of that quotient of AN. Off the top of my head, I can't think precisely what that relation is, but yeah, you're right that one should also be able to say something about those cases, I think. Yeah, but I'm not sure exactly what.
Yeah, from the covalent chamber structure perspective, right? I mean, the maximal green sequences are paths, particular paths in the covalent chamber structure.
Yes.
And then if you have a quotient, what happens is that you essentially just lose some of the walls, right? So you have a coarsening of the the fan associated to the AN. So the only thing that happens is that maybe some, I mean, essentially you have less.
Yeah, I mean, what that would sound like, I guess, to me is something like you're maybe merging some of these three-dimensional simplices together or something like that. So instead of looking at triangulations, you're looking at subdivisions where the cells of the subdivisions are contained in some set, which includes both simplices and these simplices, which are being merged together into other polytopes or something like that. Yeah, off the top of my head, that sounds like the
if you look at, for instance, I do not know how you define these triangulations for this three-dimensional polytope, but if you take A3 linearly oriented, natural quotient you should look at is A3 radical squared, right?
Yes.
That's the only quotient you have, and in this case, what would happen is that you would avoid all maximal green sequences passing through, or you need to merge
through the indecomposable that you lose.
Yeah, which is the projective injective in A3.
Yes. 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 I guess I'm not sure actually, but because somehow the way one constructs the triangulation isn't, I guess, using the way of thinking about maximal green sequences in terms of sequences of bricks. It's really sequences of mutations. So given that somehow the exchange pair of a mutation doesn't determine the corresponding brick, it's not it's not clear how those things match up actually. So maybe it's not as simple as merging simplices together.
I see.
But I mean, it'll be interesting actually. If one could figure out what the right thing to say was. Because it's not immediately obvious.
Right. No, cheers.
Thanks.
Do we have any more questions from the audience?
Yeah, I do.
Keep going.
So, what about higher slender algebras, right?
Thank you. That's a good question. So, I do very much think that the story should also extend to higher Auslander algebras, and so you can instead of taking AN, you can replace it with AND and do all of this in higher cluster categories. The problem is that I'm not sure how to prove this theorem in the higher case. Not sure how to prove.
How to find the correct matroid that you want to triangulate.
So I know actually how to define the matroid in the higher case. So the definition kind of it extends, but the proof doesn't. So
you
it
need
turns out
to
the way
have
I
some
proved this
intertwining and
theorem
something
is showing that you can reduce it to checking like 3 cases or something like that. But those 3 cases are, cases for just d equals 1, not the higher case. So yeah, one couldn't extend the same proof to all higher Auslander algebras because that would involve checking infinitely many cases.
All right.
So yeah,
Okay.
I mean, for d equals 2, one could probably run a similar proof and then reduce it to also checking some finite number of cases, more than 3, but like
Yeah, but
probably
still
still less than like 10 cases. But yeah, but it doesn't generalize. So yeah,
I see.
yeah. But I think it's still true. But yeah, I don't know how to prove.
I see. Yeah. No, very interesting.
Thanks.
Yeah, and how you define the maximal green sequences. Yeah, so very cool.
Yeah, somehow like I thought about that a lot, and it was somehow most convenient to define it like this because you're always working in the same category, namely the cluster category.
Yeah, of course.
Yeah, which is useful to do if you have to consider lots of different cluster tilting objects. And yeah, if you use one of the more traditional definitions, then you end up defining things in different categories for each cluster tilting object, and it just becomes a bit of a mess.
Yeah, you need one for each cluster tilting.
Yeah,
exactly. Cluster tilting object that takes a while.
Exactly.
And this is more of a, sort of asking the expert because maybe this is not exactly your work, but I never really sat down to understand the nuance between this extrangulated structure and the extrangulated structure of two-term projectives.
So I mean, the difference between the 2 categories is somehow that in the cluster category you have more morphisms.
Right.
Yeah, but if you kill those morphisms, then what you get is equivalent to the category of 2-term complexes, and that's a theorem of is something like Gorski-Nakaoka precedent or something like that. Yeah. So you're right that they're absolutely related. I mean, somehow if you just care about the X-triangulated structure and not the morphisms, then they basically look the same. And I guess that's somehow what I'm relying on.
They're exactly so. Once you kill that factor through t-1, right?
Yeah, well, I think what you end up killing is you end up killing all of the morphisms from like injectives to projectives. So from t shifted by 1 to t.
And then you kill those. Yeah. All right. Yeah.
Those are the morphisms you need to kill. Once you kill all of those, what you get is exactly 2-term complexes. Yeah.
Right.
Yeah.
I see. Well, yeah. Thank you very much.
Yeah. Thank you for the questions and for hosting me.
Yeah.
No, worry. Are there any more questions? Well, it would seem not, so let's thank Nicholas again.
Thank you very much.